hello all. Good morning. I think it's time for us to start. So, I think you had a very nice lecture with Roy. Yeah, he's an expert in machine and several years of experience working in the industry on the machine drives. So it's a very good opportunity for all of us that we get some experience from Roy in machine drive and all these things. And he's also developing something very interesting that can be readily used, can be used in industry. That's what you are also doing in the lab, in the emulator lab. So what you are doing, you have the model, the control that you implemented in the control card. That's what you see in the lab. We have this control card, and you can implement the control there. And the physical machine is a real machine, and from the machine you get the voltage, current, speed by different sensors and put them back to the control card. So in the emulator lab, what you are doing, instead of physical machine, you have the mathematical model of the machine inside the control card, and then you are getting the current and the voltage, all these things from the mathematical model and giving them back to the control there. So it's like almost the same as the real machine, but you don't see the real machine. And if you just do a little change there, just maybe one bit, that instead of getting feedback from the analytical model, if we change it to the real machine, then it works. And we tested in the lab that it works. So it's more like a real machine. So it's a real control as what you will do in the industry. If you work in industry, then you need to do commissioning of a drive, then you will follow the same procedure. So you had now very good overview about the AC machine, synchronous machine. Roy was discussing all these things. And I will continue the AC machine and start with the permanent magnet synchronous machine. I think Roy started last lecture, some of the content of the permanent magnet synchronous machine. So we can start from this slide. Maybe some of them, maybe the repetition from the previous lecture. And what you see, we have the machine, regular machine, and we have the coil there. Yeah, we can put now like a concentrated coil, something like we have the 3-stator coil, concentrated. And then in the synchronous machine, what we see that we have something like this, and we have the field there. We have the field winding in the synchronous machine, and we are providing, we are supplying the field current from other source, something. So there are many different ways of supplying this field current to the synchronous machine. But now we'll focus on other type of synchronous machine that's called permanent magnet synchronous machine, where instead of supplying field current here, we'll provide a permanent magnet. And they could be different types. Two of them are listed here. One is called the surface mounted PMSM. So you have the magnet on the surface. And another is interior mounted, which is inside here. So if you look at the modeling part of this machine, and you can see that the permeability of the magnet is 1. This means it's like air. So it sees the air gap is the same. So it's like a symmetrical machine. I mean, the rotor is symmetrical because the air gap here in the magnet and here, they are the same. So it sees the full air gap here. And if you look at the other one, interior mounted, yeah, sometimes you also see other type of motor, other type of PMSM, which is like we have the rotor, and there something, magnet is somewhere like this. So this could be the magnet there. But here it is interior, it's inside the rotor. And the first one we are discussing on the surface, but it's not the surface, a little inside. This also could be another possible option. So what is the big difference you see here between this surface mounted and the interior mounted machine is the air gap. So you have the symmetrical air gap here, but you have a bit different air gap. And where we have the magnet flux, and we call them usually d-axis or direct axis. So we have the direct axis here. This is the direct axis here. And if we look at the air gap, and we have the one air gap due to magnet here, and another one, this is the natural air gap. So we have two air gap in the d-axis. And then if you look at the q-axis, then we have the q-axis. This is here, the q-axis. And we see that in the q-axis, we have only one small air gap. So why you're talking about this air gap is because, and we see that torque of a machine depends on the inductance of the machine. And the inductance depends on the air gap here. And if you remember this air gap, the inductance of the machine, which is inversely proportional to the air gap. So what you see here, since you have the larger air gap in the d-axis in this machine, so you have a smaller inductance here. But you have the smaller, so we have the larger inductance in the q-axis, which is a kind of opposite to the original machine that we are discussing, where you have the rotor, which is something like this. So in this one, we are defining the axis, something like this is the d-axis. And here we have the q-axis here. So in the original machine that we are discussing, here we have the q-axis. And this is the magnet or the rotor inside, like this, not symmetrical, it's asymmetrical. And the q-axis, we have the larger air gap compared to the d-axis. So you have the q-axis, larger air gap. This means you have the a smaller inductance in the q-axis. And there's the regular machine that we are discussing. So if you also look at the inductance for the regular machine, and it was something like this for the regular machine. But now, for the PMSM, and we see that is 180 degree shifted, this inductance in the machine. So it's because the shifting of the air gap from q-axis to d-axis. So that's what we see. So why we focus on this PMSM-based machine? One advantage is that it doesn't have any coil here, any copper, so it improved the efficiency. That's the one advantage that we see. And another thing is that when you have the copper coil, there's current flowing through this. This means it's producing losses, I square R. So since it doesn't have this coil there, so the losses is much lower. So that is the one advantage that we see. And if you look at the application, and there are many different applications like, you're working on the pump, lift, and the wind turbine. So this could be application of this symmetrical machine, PMSM, and this interior mounted PMSM machine you can find in the maybe EV or traction, all these things. So those are the application. So when you design the control, this course we are focusing mainly the control, how we can design the control for this. Luckily, we don't need to work on all the parts of the modeling. There are many researchers, scientists who work on the modeling part, mathematical modeling part of the machine. So we already have the mathematical modeling of the machine. Once we have the mathematical modeling, then we understand how to implement the control. And this is very straightforward. But this course, what we are focusing the main objective that you understand how the machine works and how the control works. So this is the main objective. So when you work in the real industry, then you know that this is the machine and is how is the control inside, and this is how it works. And when you will be a researcher, maybe a scientist, then maybe you find a way, if you work on the machine, then maybe you can develop the new types of machine that can have better performance. That could be one objective for you if you become a scientist. Or if you become a control scientist, then maybe you can find an alternative control strategy that gives a better performance in terms of the controlling of the machine. So now we see that we have the mathematical modeling and then some application like this. So we have a PMSM machine. This is a wind turbine application, but it's working here as a generator. And if you see also a motor, it's also the same like. And here we have the turbine that helps rotate the machine. But other application, when it works as a motor, then we are supplying power here, and that gives the torque, mechanical energy. So in principle, we have something in the DC side. It could be a battery, or it could be a grid. And from the grid, and we are supplying through a converter. It could be controller and control converter that provide our constant DC voltage. And then this DC voltage, we are feeding to this converter. It could be PWM converter, perhaps, and providing us the voltage here. So this converter providing us voltage at this terminal, and then that gives us desired torque. So it gives us the voltage. This means we can also decide the frequency of the voltage that we can get here. And then in order to get this torque, or this energy, or this thing, or this speed of the machine, then what would be the voltage? So this is the only control input that we have. So you have to decide these three voltage, VA, VB, BC for the three-phase here. So we need to decide it. So how can we decide that voltage? This means we need to have some control that give us something that operate to provide the desired voltage. So one example here, I put one example like this wind turbine application. This is just a typical application, and what you see, we have the PI controller, and we say that we will always have one inner loop controller, and this inner loop controller is the current controller. So we have the inner loop controller. This is the current controller. And if you remember, in the DC machine, we have the armature current control, and we have the field current control. And since there's a DC machine, and we have the only one control loop for the armature current, and one control loop for the field current. But it's a three-phase system here, and there's a way to transform this three-phase system into two-phase system. And then there's some decoupling term, cross-coupling term, some feed-forward term, and all this, we have the inner loop controller. And this inner loop controller, the main reference that we give, the D-axis current and the Q-axis current. So now our task, how we can decide what would be the reference current for the D-axis and the Q-axis. And this is the control that will tell us what will be the D-axis and the Q-axis reference current. And in order to set this D-axis and the Q-axis current reference, we need to understand the operating principle of the machine. If we put some amount of the Q-axis current, does it give us the maximum torque? Or what will be the D-axis current that gives us the maximum torque? Since we have only the two control input, here these two control input, and we have these two reference, then we try to extract the maximum torque from the machine. This is the ultimate goal, to have the maximum torque. So how can we do that? So in order to do that, we need to understand the machine modeling, physical modeling. I think Roy has discussed all these things, and you are very familiar, since it's the same modeling principle that you have done for the synchronous machine. And you have the two voltage equation for the alpha component and the beta component. That's what you see. And those are for the stator voltage. And you have the stator voltage alpha component and the beta component. And now we have in the rotor is a permanent magnet. When it's a permanent magnet, that we are assuming that it has the constant field current. So field is shorted. This means there's no voltage equation for the field. Only the two armature current, only the stator voltage equation that you have. And also Roy was discussing a lot how to set up this inductor equation, because this inductor equation tells us the amount of the torque it can keep. So I don't want to talk that much about. And only thing here he was saying, and these two flux, they are 90-degree shifted. So this is the mutual flux that's induced by the magnet, and they are shifted by 90 degrees for the d-axis and the q-axis here. And then we have the physical machine. The machine equation, this is the Newton's law that we have this equation. This is a mechanical equation. And if you remember, for regular machine, we have this Lg, which is greater than 0, but now we have this is less than 0. It's because we are shifting the air gap. Before we have the larger air gap in the q-axis. Now we have the smaller air gap in the q-axis. That's what we see. Therefore, we got this one Lg less than 0. And we will discuss more what will be the impact of this thing later. Yeah, I forgot to mention that. If you have any questions, just feel free to interrupt me at any point. Just raise your hand or ask directly. So Roy was discussing a lot about also different coordinate system and how this coordinate system actually comes. If you look at the machine, it's from the machine concept. So we have the rotor and we have the stator. Yeah, maybe I should put the rotor something like this. And what we see that we have the 3 concentrated coil, something like this. This is the A axis, and the B and C. It's A, B, C, something like this. So these 3 coil in the rotor, they are fixed. They are stick to their position. This means they are not rotating. And if we supply voltage to this, and what you will see, the voltage there, they are sinusoidal. What does this mean, the sinusoidal? This means that we have the axis here. This is the axis. And the voltage at this point with time, it will go max starting from 0 and go max with time. It reaches to B peak, and then it starts reducing, and then goes other direction, and it's become B minus peak. So this axis is fixed in their position, and then it goes from 0 to max and come to negative max, and then again go positive max. And if you look at in the time plane, then you'll see it's a sinusoidal. So it is like a sinusoidal curve here, because it's starting from 0 and then going to peak and negative peak with time. But what we see that this is fixed in their position, and therefore we call this ABC frame their stationary frame, because they are fixed in their position. And some scientists, they found that we convert this 3-phase system into 2-phase, and we lose no information. They are the same. So it's because if we see in a phasor diagram or in the complex quantity, if we have anything, then we can say that like IS, and it could have the 2 components. One is the real component, one is the imaginary component. Imagine one real component, one imaginary component. That's what we also see in the power. We have the active power and we have the reactive power. Once we have the active power, then we say it's a real component, and then reactive power, then we put a J there, this complex term, and we say it's the reactive power. So what they did, we can convert this three-phase quantity into two-phase system. Yeah, in the three-phase system, for any point, like in this one, so you have this ABC. So what do you see? At a certain point, like at this point, you have this XA, something, this value, maybe somewhere here, XA, and we have also some value, XC, and we have the negative XB. Maybe some here, this could be B. So let's say somewhere here, we have the positive A, positive C, and negative B, and some of these three vectors that give us this component, this B component here. So this is the resultant vector. And it rotates, this vector is rotating with the same frequency at the fundamental frequency of the system. So it's possible to present this three-phase system into a two-phase system. Now this is in the two-phase system. What that gives us the same vector as the same as the resultant vector. Instead of three, now we are presenting with the two component two-phase system, which is alpha and beta. And what do you see that this is still in the fixed position. So instead of three, now we have two components. One is called the alpha here, and the another is called the beta. And if you convert this ABC system into alpha beta system, and then you will see the voltage, they look like this in the alpha beta. So you have the alpha component and you have the beta component there. So now we have the three-phase machine. Now we can convert it into a two-phase machine. That's what Roy was discussing a lot. And if you look at the transformation matrix, like how we can get this X alpha and X beta, and it's also possible to put the zero component, and then you will get a transformation matrix which is like 2 by 3 here, 1 minus half, 0, square root of 2, root of 2. This is XA, XB, XC. So what you see that if you have anything in a three-phase system, then you can convert into a two-phase system, and we lost no information. They are the same, equivalent. But the good thing is that instead of three-phase system, we don't need to deal now three-phase system. We can deal with two-phase system, and it's much easier in the control implementation analysis because now we have the one real component and one imaginary component in a complex plane. So that is the advantage. And then later, what we do, we see that we implement the PI controller. And the PI controller, they work mainly with the DC component. So what we can do, we can have the DC signal instead of this sinusoidal signal. So now alpha beta, here we have the sinusoidal still. In sinusoidal, they are varying all time with the time, so there is no fixed operating point. So in order to have the fixed operating point for main analysis, we convert this into a DC component. So you have the D component and we have the Q component, and still we have the same vector, same resultant vector, but what is the difference between the previous one, previous two frame, ABC frame and alpha beta frame, they are fixed in their position. Now this DQ frame is rotating. So if you look at here, this alpha and the beta frame, this is alpha and the beta, and they are fixed in their position. Now we have this D axis and the Q axis, and they are also rotating at the same speed as the vector. So the axis and the Q axis is also rotating at the same speed as the vector, resultant vector. And then we get the resultant in the value as a DC component. And therefore, we call it rotating DQ frame. So previous two, both are stationary, alpha, beta, and ABC. Now this one we call rotating DQ frame. So now we have all these things in the as a DC component. And then in order to convert this, we need to know some phase angle. So for example, here in this figure, we have this phase position, theta. This theta we have here in this position. And then we define this d-axis, q-axis here. This is the theta. This is the angle between the alpha axis and the d-axis. And then we use this information to convert them into DQ component. So in our machine, and we need to figure out which theta should we use. Sometimes we have the flux oriented. Shall we use the flux oriented, field oriented? Shall we use the stator oriented? Shall we use the rotor oriented? So all these things we need to define, and then we will see in a different application which orientation shall we use. Any question here? So what you see here, this we have the originally. This one is the. We have originally this one is the IS alpha current component, and then we compose into two components. One is this D component of the alpha component, and then Q component of the alpha component. So we have these two components for the D component. And similarly, for the Q component, we have this. We have the beta component, and for this beta component, we get two other components. One is in the Q, one is in the D component, one is in the Q component. It's according to trigonometric definition. We have this alpha component for this alpha, and we can have in the D and the Q axis orientation. So we got this Q component, and we have this D component, and we can define it based on the theta here. So what you see here, we have the theta d-axis component, and the resultant d-axis component would be this component here, and then the other component here. We have the two d-axis component, and then we can write the d-axis component, which is ISD, and we can say that ISD, which is IS beta cos of theta. This one is IS alpha sine of theta. So you have the ISB. No, sorry, this one is the cos of theta here. So we have this IS alpha cos of theta, and then we have this IS beta sine of theta. Then we got IS beta sine of theta. So that's how we can convert this ISD. And similarly, we can also write for ISQ component. And then if we present them in a matrix form, it will give us something like this, where we have this IS alpha and the IS beta, and here is ISD and ISQ. So if we have anything in the ABC, then you can convert them into alpha beta, and then you can finally get into DQ component. So once we do all the conversion, then we finally come to the dynamic equation for the synchronous machine. And for the synchronous machine, what you see, we have one equation for the d-axis component, input voltage, and the one for the q-axis component. And then we have the torque equation here, and the power equation, all in the dq. So these are the electrical equation. That's what we see for the PMSM machine. And if we also look at the stator flux linkage for the d-axis component, we have this stator flux linkage for the d-axis component. like this on the q-axis component. So we have this electrical equation and also the mechanical equation for the machine. We have this mechanical equation for the machine. So this is the machine that we developed. Luckily, we don't need to go all the development, but if you want to see, I think it's in the compendium, you can see more detail there. So this is the model now we have, and we'll use this model to understand how to implement the control and how the machine work. So now we can start with, we can look at the torque, because our ultimate goal is to control the torque. So we see the torque here. This is the torque equation. Now we have here, this is the torque equation. And we see that the torque, which is a function of the stator flux linkage and the stator current. So you have the flux and the current and the d-axis and the q-axis component. And we can also define the current, the relation between the flux and the current here. We have these two equations. So we have the flux and the current relation here. So from this torque equation, if we use this relation, we can remove the either flux from the torque by replacing here. If we replace psi d here and psi q, then you will find the torque's equation, which is like this. So now we have the torque equation, this one. So what this equation is saying to us? So we see that this is the flux link from the magnet, and it's fixed because it's a permanent magnet there. And then we have the q-axis component, and here we have the xq and the xd there. So what you see, if it's a symmetrical machine, if you remember, if it's a symmetrical machine, what would be the xd and xq? For symmetrical machine, xd and xq are same. This means it's canceling this part for symmetrical machine. So you can see that torque only depends on the q-axis component of the current. So this is the one clue that we obtained, that the torque only depends on the q-axis component of the current. That's what we see from here. And if it is a symmetrical machine, like IPSM, PMSM, interior mounted machine, then in addition to the q-axis component, it also has, maybe we can write it then, something. We remove this q part from here, something like this. And we can say this psi t. This is a fictitious flux there. This is not the original flux, it's a fictitious flux that we are obtaining because of this. And how do you see that? This xq for the asymmetrical machine is greater than xd. So this term is positive here. So in order to have the contribution from this part, what would be the value of the d-axis current? How do you see? So in order to have the positive contribution, this d-axis current should be negative, right? If it's negative, this means we get this term positive. So then it's adding to this part. Otherwise, it's a subtraction. That's what we don't want. So we never want positive d-axis current for the PMSM. We always want negative d-axis current because that gives the torque. So that is the one thing that we see from here. This means we try to have the maximum q-axis current. In some case, in the field weakening, we'll discuss that. What is field weakening later? When we need the field weakening, then we'll put negative d-axis current. That gives us highest torque. So that's the one thing that we see. And other way, it's also possible to present the torque only with respect to the flux component, and it's from here. Like in this equation, you can write that here, IQ which is psi q over xq. And if you solve also for the ID and then insert this IQ equation and ID equation there, and you'll get final torque equation, the upper one. So this is the two-way of representation of the torque, and we'll discuss the impact of these two later, why we used this representation. So now we are here in the permanent magnet machine. Now we have the machine equation, and we see that we have the two differential equation. They are d psi d dt, and this is the derivative term in the differential equation when we develop the model. And in a steady state, the differential term we put to 0. So when we put the both differential term to 0, then we got the steady state equation. So now we have this steady state equation to a steady state equation for the PMSM machine when you put the derivative term to 0. So now we got these two equations, and what we see, we have the converter that we are using to supply power to the machine. And when we convert them into DQ components, so you have only two voltage, which is UD and UQ. Yeah, this is the converter. We have the DC source, and when you convert them in mathematically, and we see that from the converter output is UD and UQ when you convert ABC to DQ. So you have the two voltage, and this two voltage we will use to control how many variables we can control. So you have the two input. This two input we can use to control two variables. So what variable that we want to control? So one is the current. This is the axis current. That's the one that we can control. And the another one is the Q-axis current we want to control. And also we see that the torque of the machine depends on these two current. In the previous slide, that's what we discussed. So we can control this D-axis and the Q-axis current based on these two input voltage. In regular operation, we will mainly focus on the Q-axis current because this Q-axis current gives us the torque. And if you remember the torque, what we see, the torque equation, electrical torque, it gives us flux, magnetic flux, multiply with IQ. And this is the one that gives us the torque for the symmetrical machine. And from that, if we have the torque, if we know what torque we want, then we can get the IQ reference. This IQ reference, which should be torque reference divided by the magnetic flux. So that's why then we can control this part. And there's some cases when you need the field weakening, and we'll discuss what's the field weakening. And then during the field weakening, we also need to control this part to provide a negative D-axis current. That's what we see. So this is the steady state operation, and if we look at the space vector diagram for the machine, this is the space vector diagram. I think Roy was discussing a lot about this space vector diagram. This space vector diagram came from this complex vector calculation. So we have this US, and thus this gives us these two space vector diagram. One is for the symmetrical machine. This one is for the symmetrical, when xd is equals to xq, and this one is when xd not equal to xq. And one thing we noticed from these two diagrams is that we have the d-axis here, and we have the q-axis here, right? This is the d-axis and the q-axis. And if you look at the current, where is the current located? And you can see current is here, right, in the second quadrant. This is the first quadrant, and this is the second quadrant. So we always place the current in the second quadrant. And we have some phase information, like here. This delta. This is the phase between the q-axis component and the voltage. And in addition, we also define another angle. This is called the pole wheel angle. It's PP. And later, we use this diagram for a bit better understanding why we are discussing these two. So for now, this is the general space vector diagram that we have now, and we will use them later for later in the next slide, actually. In this slide that we will use. And if you look at, and we say that we have the two, like we have the space vector diagram, and we place the voltage vector here, and we place the current vector here, and we have this phase information with the voltage, which we say is delta, and the phase information which is the Cp, and this is the q-axis, and this is d-axis. Yeah, this is the current Is. And if you look at the mathematical definition for the d-axis and the q-axis component, we have this d-axis, and the q-axis is the negative d, because positive d is in this direction. And you will see that we have the ud, which is minus us sine of delta, is according to the definition. So you got id and iq. So you have all this ud, uq, id, iq. They are from the space vector diagram that what we see in the previous slide, and based on the complex calculation that you can place the vector like this. So why we are looking at this here, this component, is mainly two reasons. One is that in the machine we have the two limits. The first limit is that the current. We cannot have infinite amount of current. So you have the limited current because the converter can supply the limited current, and also other thing, the current causes the loss in the machine, because the loss, if you have the resistor, every machine has a little resistor, 2-3% of the system. So this 2-3% that cause the losses, which is I square R. R is the resistor, I is the current, stator current. So therefore, this is the loss. Then we cannot have the more current. We want to limit the current for a particular operation. That's the one thing. We want to limit the current. And the second thing is that we have the limited flux. We cannot have infinity amount of flux, because if you remember the flux, we have the stator voltage, and the stator voltage, which is the, by definition, which is the speed multiplied with stator flux, and then you are getting the S max, which is US max. This is the maximum stator voltage that you can provide divided by speed. So when you reach to the limit, because you have the converter, and this converter provide limited voltage. And what will be the voltage here? This US max, it be modulation index multiplied with UDC, DC side voltage. We have the UDC here. And this modulation index could be 1 or max 1.15. So we cannot have more than that. So we have the limited stator voltage. This means we have the limiter stator flux. So if we want to have the certain speed or certain torque, then we need to work with this limited current and limited flux. So what is the impact of this torque and flux in the machine what is limited current and the flux in the torque. So we can see that we have the torque equation here. We have